Welcome everyone. I'm Joe Fine, current president of Engineers and Architects, and welcome to our Friday weekly meeting. I'll start off with, are there any announcements that anyone would like to make at this time? Any orders of business? Howard, here you go.
I am the April speaker chair, and for April 4th I've got Purnima Makushan, who's an architect who has done work not just here but in India and, are you sitting down? Mongolia. So she will be sharing architecture there. And then April 11th I have Professor Martin Despang of School of Architecture, originally German, and he brings that European flair, that liveliness that American architecture often lacks. So two very, very interesting speakers there. Then we have a holiday. Then we have April 25th, and I thought I was going to get my colleague Gail Suzuki-Jones to talk about the green initiative with hotels, businesses, and so forth, and what kind of renovations they're making, but she can't make it. But she has volunteered to speak on May 2nd. If anybody has heard of architect Louis Kahn, just happens to be one of the greatest architects in the world, there will be a movie about him and his work on April 2nd, April 4th at UH Auditorium, UH Architecture Auditorium, and his son will be there to answer questions and talk about his dad's work. I have some flyers. Are there any architects? 1, 2 going. Okay, I will distribute flyers. And finally, I serve on the HCES right now as past president, and we're supposed to hand the reins over to the current past president in April, but HCES has asked me to stay on for reasons best known to them, so I will stay on as the HCES rep. Oh, and even though we haven't paid our Wiliki dues since the Pleistocene, it's still okay if we submit articles to Wiliki. Thank you, Mr. President.
Thank you, Howard. Okay, other than our speakers today, are there any guests that we should introduce today? Or I don't think so. I think everybody's members. Okay, so it looks like we can move on to our game of skill, because I do see something in the kitty there. And we'll have our speaker choose one of the speakers to select one of the torn off tickets and read the last 3 digits. Take the money, yeah, and just read off the last 3. 189.
Hey, amazing! I got it.
Sam, congratulations, Sam. And Sam, what would you like? Donating to the scholarship fund. Thank you, Sam. There's gambling. No, not gambling. Skill. All right. Next item, that would be, I think we're up to our joke of the week. And any volunteers for joke of the week? Mac's got something prepped?
Well, I do.
Oh, here, hang on, Mac. We want to record this.
This may not be appropriate, but when has any of our humor been appropriate? And I'll read this just so I don't miss anything and make it fast. A mother is driving her little girl to her friend's house for a play date. Mommy, the little girl asks, "How old are you?" "Honey, you're not supposed to ask a lady her age," the mother replies. "It's not polite." "Okay," the little girl says, "How much do you weigh?" No, really, those are the personal questions and are really none of your business. Undaunted, the little girl says, "Why did you and Daddy get a divorce?" "That's enough questions, young lady." The rest, the mother walks away as the 2 friends begin to play. "My mom won't tell me anything about her," the little girl says to her friend. "Well," says the friend, "all you need to do is look at her driver's license. It's like a report card. It has everything on it." Later that night, the little girl says to her mother, "I know how old you are. You're 32. Mother's surprised. "How do you find that?" "I also know how much you weigh, 130 pounds. The mother's really shocked. "How in the heavens did you find that out? And the little girl says, triumphantly, and I know why you and Daddy got a divorce. And the mother says, oh, really? Why? Because you got an F in sex.
Thank you, Mac. Okay. Moving on to today's guest speaker, Gary is going to do the introduction today.
Thanks, Joe. Mac, I think that was a little bit too hard for this group. Nobody understood what you were talking about as far as the punchline. Anyway, you guys, today we're very fortunate. We have this outstanding project. In fact, it was the top award winner of the ACECH annual Project Excellence Award. It's the amazing project. And by the way, I was the head judge. So being a bridge engineer myself, I did push everybody to vote for this project as the grand conceptor, mainly because of the huge curvature on the structure and the inverted arch that made it really technically very difficult. So we have 3 project managers from Wilson Okamoto, Brian Locke, he's a civil engineer, these guys are all graduates of UH, and then Laura Mao is a planner with Wilson Okamoto, and then Eric Matsumoto is the fellow structural engineer. So I'll pass it on to Brian Locke for this amazingly interesting and difficult project.
Okay, thank you, Gary. Thank you all for inviting us to present the Honoapi'Ilani Highway Realignment Phase 1A. It's actually also known as Lahaina Bypass. Our client is the Department of Transportation. It's a design-build project. Hawaiian Dredging, the timeless Hawaiian Dredging, is the contractor. Just a funny fact on them, a neat fact on them, is that this is their 110th year. They were started in 1904. Design-build consultant team, Wilson Okamoto, led the design team, and we also did civil engineering and environmental planning. KSF, Eric over here, was our structural engineer of record. We also used GeoLabs, our geotechnical engineers. As you can see here from the rest of the team, we were a pretty highly qualified team. We had landscape, electrical, cultural and biological consultants as well. The team really worked well together with Hawaiian Dredging, leading the design and the construction on this design-build project. From that, we communicated really well, we worked well together, and it was nice to get recognition from our peers. We received ASCE Outstanding Civil Engineering Award for this project. Another notable one is the ACECH Grand Conceptor Award. I just want to go over a few project highlights before I really get into the details of the project. This is a Kahoma Bridge. It's the highlight of the project. It is a 360-foot concrete tiered arch, or inverted arch bridge over Kahoma Stream, which is dry at the moment, and the bypass highway is on top. Another feature designed by KSF. It should really say KSF Structural Engineers across the rail, the advertisement. But this is a 130-foot span, precast, parabolic arch girder bridge. It's a great separation bridge, so the Lahaina Road is on top, the bypass highway is on the bottom. This arch over here gets less than 4 inches deep. That was pretty amazing structural engineering by Eric. Unfortunately, he won't have time to go over this bridge today. We'll be focusing on the Kahoma Bridge in the latter half of this presentation. Notice that this is 4 feet here. This retaining wall is another highlight of the project. That's a 35-foot tall retaining wall that GeoLabs here helped us design. We can see we're putting in some lava rock panels over it to help with aesthetics. But the real feature of the wall is not shown here is the anchor that's installed in the heel of the footing. There's an anchor that goes about 20 feet below the wall, spaced about, I think, 15 feet on center. That was a unique design that helped us to reduce the thickness of the wall and reduce the size of the footings. These are pretty tall walls, L-shaped cantilever walls, all concrete. Another feature from GeoLabs is the geotextile fabric wall. We were able to use on-site excavated material, and we crushed it and folded it up in the geotextiles and compacted it to make fabric, to make fill walls. Another feature of the project is the high-performance concrete. Again, going back to KSF and their excellent engineering on this project, they actually tailored concrete mixes for each component of the bridge, and in this case we see them pouring the abutment for the Lahaina Luna Road Bridge. The mixes were tailored, for workability or to reduce shrinkage or to increase the compressive strength. And some of the cylinders that we cracked was over 11,000 psi. As mentioned before, the project was very sustainable from an earthwork perspective. We used all of the excavated material either on-site or on the subsequent phase, the 1B1 phase of the project. It was used as general road fill or it was used as trench backfill material. We crushed it for aggregate base course, and we also used it in the MSE walls. Finally, the project, right before the project was actually ready to construct several years ago, archaeologists discovered new terraces or archaeological features. We actually had to rush and redesign the highway to avoid and protect these, and Laura will go over that in just a few minutes. So you got to bear with me for a little bit more. This is a map of West Maui. This is the overall Lahaina bypass project. It's about 8 miles long. Our phase 1A segment is here in red and in yellow over here. We were just under a mile in total length. Taking a closer look at the project, this was the original alignment before we had to realign for the archaeological feature. The main highway is up here. This is Kahoma Bridge. This is the Lahaina Luna Road Bridge. The purpose of the project was to alleviate traffic at this intersection here, signalized intersection. Traffic would back up in both directions as people tried to access the school complex. There were 3 schools up here. After we installed the project, after it opened in April 2013, there was noticeable relief on the highway. This here is another sketch of the original alignment. Here we can see the modified alignment and the archaeological feature that we avoided. Again, Kahoma Bridge is here. This is Kahoma Stream. Lahaina Luna Bridge is here. There's an off-ramp loop, and the Keawe Street extension was also incorporated into the project. And from here, I will give it over to Laura. She'll tell you why we did this crazy thing.
Thanks, Brian. So as Brian said, we were ready really to start construction. We had received NTP on this, and we had gone out to the community already, and we thought that public information meeting was to give notice to the community that we were going to start construction. Just prior to that meeting, however, we had a routine meeting with the State Historic Preservation Division to go over what had previously been done with all the prior archaeological studies. At the time, all of the environmental clearances were completed, and again, FHWA and DOT thought we were good to go. As a result of the meeting with SHPD, Wilson Okamoto and the archaeologist, Cultural Surveys Hawaii, went out and did subsequent field survey and found that there was an additional archaeological site that was previously undiscovered. It turned out to be a very massive agricultural complex shown here in green. It's approximately 33 acres, a portion of which was right in the original alignment down here. The red line denotes not only the slope easement here, but also the new right-of-way that was going to be, that was actually created for the project. Down here shown in green was a previously discovered L-shaped enclosure that was already inventoried, and we thought that one was good to go as well. To our surprise, this is that same little green square. The portion that was previously discovered really entailed only this outside wall, but when we did a little more homework, we found that there was a very intact system of agricultural terraces and awais. And much of this was dated back to pre-contact times as well, so it was very significant. And this was that prior picture that Brian had shared with you. You can see here very defined rows where the terraces were. This is Let me back up. The next set I'm going to show is close-up of this little purple area that was directly impacted by our project. And that site was noted as Site 6277. And again, it turned out to be a very well-defined complex of agricultural terraces and an intact awai system. The area shown in the yellow band is the slope easement. The area in the brown band is the new 150-foot right-of-way. So clearly we were impacting a very significant portion of this complex.
Was this taro?
They think it might have been sweet potato. They weren't sure, but prior to the sweet potato, we were not sure what was farmed there. Because we had these new finds, like Brian said, we had to realign the roadway. And what happened was in doing so, we had to redefine the new area of potential effect, which is shown in the yellow band. This includes the new right-of-way as well as a pretty wide buffer on both sides. And we did extensive trench testing shown by all of these purple demarcations. The trenches all came back clean, but we did find some surface features which involved these agricultural push piles. One of the lessons learned on this project was that previously we thought agricultural push piles were considered insignificant, previously disturbed materials. We also thought that previously agricultural plowed lands were also fairly insignificant because they had been disturbed. What we found, and one of the lessons learned on this project, was that in fact there could be subsurface sites below the plow line, which was the case with another project further downslope of ours. What was the result of these new discoveries? We had to go through, or DOT had to go through a number of regulatory triggers, two of which were state and federal EAs and compliance with Section 4F of the Department of Transportation Act. And Section 4F administers public parks and recreation areas, public refuges, and historic sites. So in our case, the trigger for Section 4F was the historic site. And what this requires is that the federal agency go through avoidance, minimization, and mitigation measures with respect to the resource that's being affected. I'm going to focus more on this last trigger, which was Section 106 of the Historic Preservation Act. It was a very challenging process for us to go through. Basically, this requirement is triggered anytime you have a federal undertaking where you have federal funding, you have a federal action, or a federal permit. The process needs to be completed before FHWA or any other federal agency can authorize the project, and it requires consultation with all of these major groups, including at the federal level, the Advisory Council on Historic Preservation, the SHPO, as well as Native Hawaiian organizations and the public at large. We did extensive consultation with a number of NHOs, or Native Hawaiian organizations. It included lineal and cultural descendants who had direct ties to the 3 ahupua'a that were being affected by the project. It was a very sensitive issue, and it created heightened sensitivity just because of the nature of the project. We got to meet with some of the families on a very intimate level.
Just to mention one more thing is Lahaina was the leading area, so the land tied back to so royalty and rights. These people were very passionate.
We also consulted a number of public agencies that are key with regard to stewardship of archaeological and cultural resources. This is a photo of the team meeting with the then members of the Maui Lanai Island Burial Council. And it was really one of the first times we had ever gone out in the field with a group like this. Behind the scenes, not shown in the picture, are some of the lineal descendants. And again, it was just a very passionate meeting. There was a lot of emotion that was evoked because of this project.
Kind of emotion.
Like Brian said, it was because of their cultural ties to the land. Many of them have been there for generations, and to have the knowledge that this project was going to be going through and that it could possibly bring additional development was just a very sensitive topic for them. Many of them still access their native lands. In one of the earlier maps I showed, there was quite a number of archaeological sites that are farther Mauka of where we are. Some of them are family burial plots. I think what it really evoked in the family members was a sense of stewardship they were given this responsibility to steward their family's lands, and to see it developed in this way was particularly emotional for them.
They were united, they were for it that day.
You know, that was an interesting thing. In consulting all the groups, there was a pretty marked divide between the Hawaiian families. Some were supportive of this project, and some were very opposed to it. And it was just very difficult to get consensus with this group. And we held many meetings with them. Some meetings we had to schedule carefully because certain families would not be in the same room with other family members. So that was also a very humbling learning experience for us. We also...
And this was just for that 1 mile part, right? I mean, the new road was many miles.
Correct.
So there were archaeological studies and negotiations for the rest of the road independent of your work.
Yeah, the next phase, the one south of us, is phase 1B1. They also encountered some of the same family members. But what we did was, with the lessons we learned, we met with subsequent design team to help them create a strategy and an approach to dealing with the same family members. And we also kind of ran interference, and we were liaisons between that group and the family members to let them know that the next design team was going to come on board, so they would know to actually answer the phone when somebody called. One of the challenges I had personally was I had sent out many emails, called many people, but did not get any response back from them for a couple of months. And it wasn't until one individual called me and grilled me for about 3 weeks, did his due diligence on Wilson Okamoto. Once he could vouch for me, he spread the word through his Coconut Wireless network, and then we were flooded with calls and emails. So that whole process just took a lot of time and patience. In addition to the Section 106 consultation, we did extensive community consultation. We held 3 public information meetings. They were very well attended, and we had really great input from everyone. Part of the success of those meetings, I think, was because we did a hybrid format, which included an open house portion in the beginning of the meeting, and then we did a group session here. So if you can see, there's a number of people here, and then in the background is that open house format. I think it really helped to open up the floor to people who wanted to speak to us individually. We had different sections opened for people who wanted to come and speak to us on certain issues, but then we could all come together as a group and meet here. So I'd say on average our meetings were attended by between 200 and 300 people, and the feedback we got from DOT was it was really the highest attendance they had on any project in the past. But I think in doing so it was successful because the community felt more involved and more supporters came out. I mean, often you hear the silent majority stays in the background and the vocal minority come out. But in this case, we had a lot of supporters come out and help DOT. So it really worked for us. In addition, we also met with extensively with different agencies and organizations. We met with the school complex because they were directly affected by this project. We also met with civil defense and first responders because they also had a lot of issues in the past with emergency access. A lot of times there's fires up there and they can't get through. The road needs to be closed. So they too were part of the vocal majority that came out to support us. Lahaina Bypass Now was a key organization that really helped DOT in getting the word out through their network and getting supporters to come out. And many of their supporters were also members of these other groups. So I think all told, it was a really positive experience for us. It was a big challenge. Again, it was very humbling, but it was rewarding, and it was a successful project as far as DOT and FHWA are concerned. So that's all I have. I'll turn that back over to Brian.
Yeah, so before I let Eric loose on you, I just want to go over a few of the alignments that we looked at to avoid, minimize, and mitigate. So this is the first alignment here that one of the alignments that we looked at. We tried to reroute the highway to avoid the archaeological resources, but by doing this, we took a lot more houses and it was a big impact to the community. So we eliminated that. Another one that didn't take any houses was a cane haul route alignment following an existing cane haul road. There would have been no impact to homes. It would have been a good alignment. However, the existing highway is right next to it. It really negated the effect of a bypass, and that's why this was eliminated.
Those have a higher potential of getting land commission awards and more additional archaeological resources.
Yeah, that's correct. This is another alignment, shorter realignment that additionally took, another 50 homes in this area, but it did avoid the highway, but it was eliminated because of the impact to the homes. This is a couplet alternative, so we tried to narrow the right-of-ways to minimize the amount of homes that would be taken, but we still had to avoid the site, so we still took homes here and we took homes here. So it wasn't eliminated, and it was a higher cost option because now we had 2 bridges crossing the stream. So this, again, is the original one I showed you before, and that's how we turned the highway to avoid the archaeological resources. Now you guys know why we did that. It's one of the, maybe not the first time, but one of the few times that DOT has listened to the public, has tried to preserve a significant cultural resource, and we actually made some drastic changes to this highway. We made a T intersection. It's signalized in the future. There is a free flow right in the past, but our project was basically this portion all the way up to the off-ramp loop. This is the next phase, 1B1, which has been constructed. From here on, this is phase C. Hasn't been constructed yet. But the most drastic effect was to Kahoma Bridge. Now, in order to save the homes, we had to turn the highway over the bridge. And that really messed Eric up. Really made me happy. But it significantly changed the structure. It super elevated the deck. A structure that was previously uniform was now curved, and all the pieces were different. So I will let Eric loose on you now and let you know how he solved all those problems.
Thank you, Brian. So Lahaina bypass crosses Kahoma Stream with a low-profile 360-foot single-span, 60-foot wide inverted tide arch bridge. And it consists of a unique combination of precast, post-tension, and cast-in-place concrete. The final configuration evolved through the consideration of material strengths and capabilities, utilizing concrete compression members and post-tensioning strands. Here's the picture of the bridge, and our elevation of the bridge in plan. And this is our cross-section of the bridge. On the right side, you see a potential future bridge. The bridge bottom chord consists of 10 lines of precast arch-type planks, or PATPs, that are joined together with post-tension strands. Post-tension strands are anchored at the abutments, or end blocks that are located at the abutments. So if you can imagine these PATPs as dried pasta, and you put a piece of string through it, and when you yank it up, it goes up. So this bottom chord, or the PATPs with the post-tensioning, provides a lifting force for the bridge. The top chord consists of precast concrete deck panels, precast concrete tub girders, and a cast-in-place deck. The concrete girders run longitudinally with the bridge and span between the concrete bends. On top of the girders, we have precast deck panels. These components are then tied together with a cast-in-place deck. The bridge top and bottom chords, along with the post-tensioning, are then connected to the end blocks at the 2 abutments. The cast-in-place end blocks also contain friction pendulum bearings. This allows the bridge to move, whether it's seismically or temperature and shrinkage. In the final configuration, the bridge is self-anchored. Again, the top chord directly supports the vehicular loads, which are then transferred to the bends into the bottom chords, the PATPs, which are taken back into the end blocks and down through the friction pendulum bearings and abutment footings. We spend a great deal of time constructing a 3D finite element model. Some of the engineers probably know Dr. Harold Hamada. He worked on this 3D model for quite some time, and we went through a number of iterations until we felt comfortable with the results. Once we were comfortable, we focused on the elements. Also, these elements were modeled in our LUCES program, and this allowed us to understand the overall behavior of the structure and each component, and to address the issues accordingly. The analyses also accounted for the different phases of construction: transportation, bracing, and final configuration, to name a few. As for the results, just to give you an idea of the forces and moments we were designing for, the dead load of the structure is about 18 million pounds. And since this bridge is on a curve, it wants to twist to the outside. So if you would imagine like a half of a hula hoop, if you were to hold the ends, it would turn to the outside of the curve. And this twisting was about 80 million foot-pounds. And the axial in this top chord, where it compresses in, was about 36 million pounds. So we also designed the falsework, which included sandjacks, steel bracing, and to account for the loads and stability of the structure throughout all phases of construction. And here's an elevation of the bridge with falsework as shown on the plan. We also designed the truss to span Kahoma Stream. The length required for this truss at the bottom was about 65 feet. We were then able to construct bends 4 and 5 without any disruption to the stream below. The truss was designed for about 1.6 million pounds at each bend. We also needed to account for the loads, the lateral loads and vertical loads, as well as the displacement of the structure throughout each phase, as well as the placement of precast members above and the behavior of the structure. And here's our design for the support of those PATPs, or the dried pasta portion. When we had to also account for the slope of the arch-type planks, you may have noticed the bottom chord was a parabolic shape. So we had to make sure that these pieces did not slide downhill before they were connected. And you may notice that we have some cylinders in that yellow circle at the top of the towers. These are sandjacks. The sandjack is a steel ring that contains sand. The sandjack serves as a temporary support such that we can build the structure at a certain elevation. And once the structure is complete, we can lower it in a uniform manner. We also designed the apparatus to test these sandjacks. Here are the steel ring pieces, or steel pieces that were put together to form a ring. And we also tested the sand to see which type is most appropriate. The one we selected was a fine manufactured silica sand, so extra precaution had to be taken so that it would not be inhaled. And here we are, placing the sand, making sure that there is no moisture. We then tested the sandjack for low capacity and displacement. And here's a closer view and another view of the test. We also went through trial runs until we were confident that the sandjacks could be used. Here the sandjack was released, and the sand came out, and the 2.5-ton block above it settled uniformly. So no problem, right? And here's a picture of abutment 1 looking towards Kahului, waiting for the concrete to be poured. And at each abutment we placed 2 friction pendulum bearings to again accommodate movement of the structure. The bearings were placed between the abutment pedestal and end block above. While we're placing the falsework, Hawaiian dredging started with the precast. All of these precast components were fabricated in the contractor's base yard about 2 minutes away from this site. But if we were to precast these they would either come from the mainland or Oahu, and it would have to make the 1-hour journey from the port in Kahului. So you can imagine this route contains numerous horseshoes and tunnels, so there would be a lot of disruption to the traffic. So now I'll go over the individual elements, starting with the precast arch-type planks. And here's an aerial view of the PATPs. These PATPs contain the ducts for our continuous post-tensioning, or the tendons that run from abutment to abutment. These are the pasta pieces that we put the string through. And during the construction of the bridge, the PATPs were also used to brace bend forms. We have 80 of these members, approximately 40 feet long and weighing about 20 tons. And here's a picture of the workers finishing the top of the PATPs. We then cover and shade the newly cast piece. These planks were post-tension for its simply supported condition for transportation. Also, as I said, the bracing for our bends. There were 4 strand tendons for this load case. And here we are, Raymond stressing each tendon to about 44,000 pounds. And here we are setting the planks. another view of the planks being set. And this is the last of our PATPs being set. And here's the photo of the PATP being used to brace the bent forms. So on top of these PATPs, we put super studs, which were anchored by inserts, and then we put that pipe to brace the bent forms while we were pouring the concrete. These planks are then tied at each bend with stiffener beams, which contain mild reinforcing and was used to splice the post-tensioning ducts. And then here's the transverse view. You can see the lanai in the background. The one good aspect of this bridge is that the main structure is below the roadway, such that it will not destroy any views of Molokai or lanai. And here's a longitudinal view of the stiffener beam. These beams provided the lateral stiffness for the bottom chord and served as supports for the bends. And the connection between the bends and these bends and the stiffener beams were designed as a hinge. So in our analysis, we found that a small and minute movement at this point significantly reduced the moments in that bottom chord. So we placed a small layer of epoxy. And in this next photo, we have Johnny putting on the epoxy. And the analysis also showed that in bends 1 and 7, or the ones closest to the abutments, there was a significant tensile force. So we clamped it down with vertical post-tensioning. And so the PATPs are this is the photo of the vertical post-tensioning at bend 7. So the PATPs are in place, the stiffener beams cast. Now we are ready to cast these bends, which are about 12 to 25 feet in height. While the bends were being constructed, we also cast the bottom portion of our end blocks. This is where all the forces from the top chord, bottom chord, and the reactions converge. And this is also where the post-tensioning is anchored. And here's another view of our post-tensioning. So once the rebars are set, we're ready to pour the concrete. And the bottom portion of our end block is backfilled with a geosynthetic reinforced soil system. And now we are set to place the girders. We have 48 tub girders. And here's our section view of the girder. They're about 40 feet long, weighing about 30 tons. And these were designed as column pieces with torsion. Here's a view of the casting operation. The reinforcing, because it is a compression member. Then we vibrate the concrete. And then we cover and cure our newly cast member. Here we are setting the girders. And another view of the tub girder placement. And to tie these tub girders to the bends, we pour this cast-in-place piece. And finally, for our precast elements, we have the precast deck panels. These panels sit on top of the girders and function as stay-in-place formwork. There are 132 of these members, 3.5 inches thick by 18 feet long. Again, this top chord is a compression member, so the steel requirements. We then cover and cure our newly cast member. Wet burlap is placed over it, and then a tarp is placed over the burlap. And here we are lifting the panels. Then we set the panels on extruded polystyrene. Here's a view of the deck reinforcing. The steel requirements, it is a compression member, and the finished deck. And now we're ready for the post-tensioning. And here's the layout of the post-tensioning anchors at the back of our end block. We had put more force in the tendons on the outside of the curve to counteract the twisting. And here we are cleaning the ducts. We place the hydraulic jack over the tendons, and then we are able to post-tension. We then grout the ducts, and now bridge is completed, and we have to release our FALSEWORK. So the moment of truth. We did give the contractor the sequence to release these sand jacks such that it will not overload the bridge in any way. And a cross-section of our bridge where we show all our sand jacks and the sequence in the Mauka and Makai directions. And Harold Homada also checked this 3D model out such to verify that the release of the sequence of the release was safe for the structure. And Hawaiian Dredging said, to show confidence, you have to stand underneath the bridge while they're releasing the sand jacks. So I was there with them. Unfortunately, moisture caused a problem, so the sand was a little hard. So what we did to resolve this issue was add more moisture. So with the water, the sand was able to come out easily, and then the shoring towers were able to be lowered in a uniform manner. And here the bridge is settled into a final position. We then pour the end beam enclosure, finish with our backfill and the approach slab. We perform grinding and grooving of the deck, and we finally cast our railings. These were architecturally designed, by the way, to present a more pleasing structure. And here's our as-built view, and a closer look at our architectural rail. Then we have our before picture looking towards Kahului, and the final structure. Okay, thank you. I'm sorry, I think we just got it under 1 o'clock.
What did it cost?
So the official cost for this bridge was probably about in the $18 to $20 million range, but the contractor would not provide a complete breakdown, but that's the range that was given to me.
Yeah, so the initial project cost was about 49 million, and then the final project cost after we realigned everything was close to 8 million.
Okay, you folks, that was one fantastic project. And now you know why I convinced my fellow judges to vote for this project as the grand conceptor. Anyway, Brian Locke,
Thank you.
and Laura Mao, and then Eric Mutzmore. Okay, guys, very good. Yeah, this certificate, by the way, is very important. You know, we've been doing it since 1902, so we're heading for the next 150 years. This year is already 112.
We're older than Hawaiian.
All right, that concludes today's meeting. Thank you, everyone. We'll see you next week, where we're having, what's next week? Anybody have Gary next week?
Hirota. Yeah, Sam Hirota will be, not Sam Hirota, but Dennis Hirota will be talking about the huge city project, pothole identification and repair. Yeah.
All right, thank you, everyone.
I promise to show up.